constrain the system to keep this particular volume element fixed in time. So exactly the same volume element that's in here equals Bm and says, let's keep this measure Bm time independent. So that's a little funny as a variational problem, because then where's this fixed volume condition coming from? Is it a part of some gauge fixing condition? Or how do you actually make it consistent with the rest of the story? Besides, it's nice that the right-hand side follows from a variational principle. That's certainly progress. And the f function itself indeed exhibits very interesting monotonicity properties, which were very helpful in proving Fermat's theorems. But it's kind of interesting to me that they really are so interested in deriving the right-hand side from the variational principle, but they never ask where's the left-hand side of the equations coming from. Is that also coming from the variational principle? Okay, but this will be our starting point. We'll try to find a topological quantum gravity which localizes in its path integral to this system of equations, or maybe a generalized system with more couplings available to us. And then we'll ask, what is the place where this f functional appears, and what is the meaning of this dilaton field phi, and where is this fixed volume condition coming from, so that we reproduce the correct equation. So this idea of the Ricci clause, as I said, is important for topology. There are a list of conjectures that have been proven already using the Ricci clause, and it's interesting to physics, not just because it gives you some controllable description of a time-dependent cosmological geometry, perhaps embeddable into quantum field theory, but also because the Fermat f functional and the other more advanced functions he introduced later often play the role of entropy in some well-defined mathematical sense. They typically have some monotonicity property on the flow. And in particular, as you can control these functionals, what that leads to in the mathematical literature is a very precise control over space-time singularities. This, to me, is the, if not the first, then at least one of the first possible areas where you can, in some precise sense, control all possible changes in the spatial topology in some quantum mechanical gravitational path integral. So we certainly want to take advantage of this classification of the space-time singular behavior with control of topology change. In the mathematical literature, this was for a long time called Ricci clause with surgery, but the surgery is not quite an honest topology change. It's a topology change up to some regularization where you have to step in at some point and perform a surgery, and then you follow the evolution of the equation further. In more recent years, various mathematicians have introduced the idea of singular Ricci clause, which is a refinement of the Ricci clause with surgery, where they can define what they mean by a weak solution of the Ricci clause equation through the singularity and follow it through at all scales, not just cutting off at some epsilon distance away from the singularity. So a lot of that mathematical control is available. Just to give you some preliminary feel for how the Ricci flow works, if you start with a Ricci flat manifold, so for simplicity I've drawn a torus here, but if this is true in any dimension, of course the Ricci flat manifold will just stay static at all times. So in my drawings, time will go up, as in GR typically. And this is, of course, the simplest, most boring type of Ricci flow. Then you can have manifolds of a positive curvature. Let's say you're interested in 3 + 1 dimensions in an almost round 3-sphere, or a 3-sphere which has positive sectional curvature everywhere. And then you can prove what that sphere will do, even if it doesn't start as completely round at first. It will round itself, and then it will collapse into a point-like singularity with the entire volume collapsing at a single time. There is no anisotropy in the singularity. So this type of singularity is certainly possible. And if you start with such a manifold, which has only positive curvature, this was already known to Hamilton before Fermat, you reach a finite extinction time and there is no semi-classical geometry past that singularity. So these are, in some sense, trivial singularities, and I'll address how they appear in the topological quantum field theory once we build that theory. And then there is a third type of general behavior, if you start with a manifold which is negatively quote-unquote curved everywhere, some kind of a, let's say in 2 dimensions, a Hardy-Riemann surface with some hyperbolic metric on it, it will just keep expanding forever. So those are the generic types of behavior, and then you can ask what happens if I have a more complicated manifold where there are some regions which are positively curved, some regions are negatively curved, and that's where interesting singularities will start appearing. So for example, if you start with a sphere, but pinch it a little bit, put like a kind of a belt around the sphere, so the region near this small circle is locally carrying negative curvature, then what happens, and this is specifically true of 3 dimensions, but in principle higher, 3 spatial dimensions. So let's think this is a 3 sphere, for example. If you start with this slight deformation, slight pinch of the sphere, what happens in some finite amount of time, the pinch will develop a singularity. This is known as the neck pinch in the math literature. And at some point, this is where you want to be regulating the solution in a sense. But then what happens is you can provide a unique prescription how to extend the flow through this neck pinch singularity. There is a topology change in space. The original sphere splits into 2, and those 2 spheres will round themselves up and then disappear into a singularity in finite time. So in order to control this, we can zoom in on the region near this neck pinch singularity with the topology change. And so what a mathematician, and of course also a physicist who wants to regulate these background solutions, will do is to look not exactly at the singular time, the time slice where the singularity appears, but just slightly before the singularity there is a connecting cylinder like this. So this is an S2 cross an interval. We are in 3 spatial dimensions. And then you cut off this yellow piece of the geometry, replace it by hand with 2 disks. So this would be an S2 filled in into a 3 disk, 2 copies of that. Once you perform this substitution, you can then restart the Ricci flow and show that the rest of the geometry evolves not in a non-singular way. In order to control this type of neck pinch singularity, you want to be defining a good way of zooming in on the regime where the singularity is actually happening. So for the Ricci flow with surgery, people actually control by scaling models, basically scale away all the outside features away from the singularity. And this particular neck pinch singularity would then look like starting with an infinitely long cylinder, and then the cross sections are 2 spheres, and the 2 spheres will then start shrinking in a uniform way until they reach a homogeneous singularity along the transverse direction. So this is an example of a singularity which in this technical sense is actually happening only in 2+1 dimensions. The 3rd dimension, the infinite transverse direction, is just a spectator. It doesn't get singular. The metric along the 3rd direction doesn't change. It's just the 2 dimensions along the 2 sphere together with time that get involved in singularity. And that might be an important point because this is just a simple example, but there's a mathematical theorem, one of the most beautiful ones in this literature of the Ricci flow, where they have proven that this is the generic behavior. You can have either these volume collapsing singularities where the entire free volume of a positively curved geometry collapses per point at the same time. Those are in some sense boring. And then every other singularity has this effective dimensional reduction feature that happens on 2+1 dimensions, with the 3rd one being just a spectator. Okay, so now let's start building a quantum field theory. The goal is it's going to be some topological quantum gravity, hopefully localized to some Ricci flow equation, so that instead of instanton moduli spaces in 4-dimensional super Yang-Mills, here you would have the spaces of solutions of the flow equation. So if I'm expecting the space-time to be a foliation by these of constant time, and for now let's, as I said, keep sigma the same and address the topology change only later. So for starters, I'll take the space-time to be just the direct product of the spatial slice times an interval, and this is just topologically. I haven't put a metric on it yet. I'll want the theory to have a topological BRST charge because I'll be postulating that all metrics Gij, so Gij is a metric on space. Ij are the spatial indices going from 1 to d. So the BRST charge will map the metric to its topological ghost. This is a gauge fixing of the topological symmetry. I'll also have to introduce the gauge fixing condition, and of course I want the gauge fixing condition to be the Ricci flow equation. Therefore, because the Ricci flow equation has the same tensor structure as the metric itself, the anti-ghost and the auxiliary field will also have to have the same index structure. And then it turns out to be extremely useful to constrain the structure even further and postulate not just n equals 1 supersymmetry with the Q supercharge, but because of this symmetry between ghosts and anti-ghosts, you can anticipate n equals 2 supersymmetry with a bigger superfield. So now I have theta, theta bar. They are not complex conjugates, they are two real variables, just for historical reasons called theta and theta bar. So the bar is more like an index rather than complex conjugation. So I have the metric, its ghost residing in the theta component, the anti-ghost and the theta bar component, and the auxiliary and the theta theta bar component. Building such topological theories with n equals 2 supersymmetry, where besides Q you also have a Q bar supercharge that would map the metric roughly to the anti-ghost. That's not uncommon. Such theories are known actually by a specific name. They're called balanced theories in topological quantum field theory literature. There are two examples. Typically they calculate the order number of the instant moduli space of the underlying equation. So to summarize what we have started with so far, we have two supercharges, Q and Q bar. We also can introduce the conjugate superderivatives. And our superalgebra is designed such that Q and Q bar anti-commute to the time translation. And Q squares to 0 because it's a BRST charge. And Q bar, which is kind of the anti-BRST charge in a sense, also squares to 0. So it's a simple superalgebra, but still, this theory can get quite involved because we'll have not just the original matter fields of the gravitational field Gij that I introduced here and its superpartners, but we'll try to make the theory as gauge invariant under as many physical symmetries as we can. So for starters, we can construct the most primitive topological gravity theory with these symmetries and already localized to some kind of a Ricci flow. And it will take the form in superspace of a Lifshitz-sized non-relativistic gravity field. The fact that I was very interested in introducing some 10 years ago, and I'm still very interested in understanding their quantum properties better. Their action is typically possible. It's possible to write the action as a sum of two terms. One of them you can think of as the kinetic term. That's where time derivatives of fields will show up. And the remaining part is a superpotential. In our case, we'll call it superpotential for short. It will contain all the terms that don't have time or super derivatives in it. So the kinetic term, if I'm interested in writing down the lowest order as an effective field theory would in the expansion in the dimensions of operators, I know I can write down two independent contributions to the kinetic term. This is exactly like in the bosonic non-relativistic gravity where you have, except little g, you now have superfield capital G, but other than the structure of the terms is very similar. There is dg bar, which when you do the superspace integration over these two super dimensions, this will give us a term which has time derivatives in it, so that's why it's a kinetic term. This structure is unique. If you wanted instead a structure which has the same dimension, which would have one time derivative and no super derivatives, that would always be a total derivative in superspace. So that's disallowed, or it's a topological event.
Should I think of this inverse G as how should I think of that? Is that like the super field inverse?
Right. I'm assuming that Gij is an invertible metric, so we can invert order by order. So the leading term of Gik will be the inverse metric, and then the rest comes just from the Taylor expansion. And right, so you certainly have these dg bar pairs in all the kinetic terms that you can write down without them being total derivatives at this order in the of operators. But there are still two such different terms that you can write down depending on how you contract these indices. This object in parentheses here is of course the supersymmetric version of the well-known David metric from the theory of gravity, where you know that on the space of metrics we can have a one-parameter family of metrics parameterized by a coupling, which is typically called little lambda. And in general relativity, if you were writing down the analogous kinetic term in the non-relativistic rewriting of GR, this little lambda would be locked to be equal to 1 by space-time diffeomorphism invariance. Here we will have fewer symmetries. In fact, this theory so far has no gauge symmetries besides the topological symmetry. It does have global spatial diffeomorphisms, which are time independent as a symmetry, but that's more of a global symmetry. It cannot be so far made time dependent, so you shouldn't think of it as a gauge symmetry. But it is spatially diffeomorphism invariant and time independent diffeomorphisms. That's the requirement for the construction of the action. And then the superpotential, you can go wild and write down any arbitrary number of terms in the superpotential as long as they don't contain d or d by the d bar derivatives or time derivatives, and that's good. They will belong to the superpotential. And the question is how far you want to go, how many derivatives you are willing to allow, and we will be interested in stopping at 2 derivatives. So we'll have a cosmological constant-like term, which is just a constant. And then we'll introduce the one and only dimension 2 object in spatial derivatives that we can have, and that's the spatial Ricci scalar with its own coupling. So that's the entire primitive theory, and it already is somewhat complex because it has 3 couplings: the cosmological constant, this alpha r coupling, and the lambda coupling in the kinetic term, and besides an overall coupling kappa squared in front of the entire action. So if I choose to make little lambda and alpha r dimensionless, I can. This will define for me an actual scaling which will be characterized by the z equal to 2 dynamical exponents, so time scale half as fast as space, in which case alpha lambda would be dimension full, but also if you are in dimensions other than 2 plus 1, kappa squared would be a dimension full coupling. So if you are in 3 plus 1 dimensions and allow z equal to 2 scaling terms, truncating at second order in operators here, then kappa squared would be a non-renormalizable coupling in power counting sense. Which, whether or not that's important is a good question, because normally power counting renormalizability is interesting for theories where you know you will have to calculate in principle up to arbitrary root order and make sure that the theory doesn't get out of control, or whether it has to be treated only as an effective field theory valid under some fixed coupling cutoff. And but here it's different because this is designed to be a topological theory. So you know that once you find the correct moduli space of solutions on which the path integral is localized, the one loop calculation should be exact, and therefore you're not really forced into performing some complicated multi-loop calculation. So what does it mean for the theory to be self-complete at short scales is a different question, and I think it should be decoupled from power counting renormalizability. But it's true that if this theory is written down in dimension higher than 2 plus 1, it's not power counting renormalizable for whatever that's worth. Unless you start, of course, adding higher terms. And there will be beautiful terms you can start adding. For example, in 3 plus 1 dimensions, if you add the Chern-Simons 3 form to the superpotential made out of the Christoffel symbols of the spatial metric, then it will give you the Coton tensor in addition to the Ricci tensor, and you get a third order flow equation. And that would be power counting renormalizable in 3 plus 1 dimension. Okay, so now we can.
So this is obviously topological because we're going to take Q through the BRST.
Yeah. In
this whole action is BRST.
Exactly. Yeah, this is BRST exact. There is no other BRST non-exact invariant other than topological invariance that you can add to the action. So all the standard arguments of topological field theory will apply. The semi-classical approximation will be exact if you are asking about correlation functions of BRST invariant objects. And it's interesting to see what the localization locus will be on which the path integral localizes. So far, we just introduced a few lowest terms in the superpotential and the unique up to the choice of lambda kinetic term, then the next thing that we can do is to actually identify the localization equations. So the equation of motion for the system would be of second order in time derivatives, and they would be, so let's actually do it in components. So the kinetic term written in components boils down to that same David metric now for just the bosonic fields, times a term which is quadratic in the auxiliary field B. And if you see immediately, if you integrate out B, you'll get a second order in first time derivatives kinetic term as usual in a Ricci theory of gravity. On the other hand, B appears linearly also in the superpotential, and it multiplies the variation of the superpotential, or at least the bosonic version thereof, with respect to the metric. So the equation on which the theory localizes turns out to be the equation where Bij is 0. So just like in the case of topological Yang-Mills, even though the Yang-Mills equations of motion are of second order, the path integral of topological Yang-Mills localizes to the first order instanton equation. Here, this is exactly like that. The equation of motion would be of second order in time derivative, fourth order in the spatial derivatives, but the localization equation is just a flow equation in this form. Lambda tilde is kind of the dual of this little lambda, because now we have the David metric with the indices down, so it's the inverse David metric with the one upstairs. And it's kind of curious and nice to see that even though the original Hamilton equation was not an equation of motion that would follow from a variational principle, that probably is still true. There are proofs, elementary proofs that that's the case. In our setting, the precise Hamilton-Ricci flow actually follows as a localization equation for this primitive theory. And that doesn't seem like it's too much, but it's still interesting because it actually resides in the existence of this variational principle for the entire equation rather than just for the right-hand side, which reminds us that in order to say that the metric flow with the indices downstairs is controlled by the variation of a functional with respect to the metric, you of course have a mismatch of indices, and you have to decide what is the type of metric on the space of metric that you use to lower or raise the indices from one side and the other. And there's this parameter lambda tilde which is available to you. So if you choose it to be 1 over d minus 2, it turns out that for the obvious values that alpha r has to be 2. This is just Hamilton's original normalization. And we want to turn up the cosmological constant by fine-tuning here. We get exactly Hamilton's Ricci flow as a localization equation.
I didn't understand. So what's W? It's not the superfunction.
It would be, if you take SW and just, if you take SW in the super,
Partial derivative of that lowest component.
yeah, if you take the lowest component of this object, then that's what I call W.
Before doing the derivative.
Right. Just forget that these are all super fields.
Right.
Declare them to be just the bosonic component and forget the integral. That's essentially where this came from, because this is the ij is the theta bar component. This is what came from the rest of the superpotential. So the superpotential and the n equals 2 supersymmetry here is crucial in order to get the right-hand side of the flow equation to come from a variation of something. But also the fact that the kinetic term contains this structure is crucial in order to allow you to have this extra.
What was that again? I didn't understand the lambda tilde.
So this is the David metric on the space of metrics with the indices down. It has its own inverse on that space, and that has the form, or four indices are down, and this lambda tilde is something like lambda divided by 1 minus b lambda or some combination. They are uniquely determined in terms of each other. And this is the traditional notation. Instead of writing the equations in terms of lambda, they would be much more complicated. It's common in the Ricci gravity literature to call this parameter lambda tilde.
And the fermionic sector is completely boring, right?
Yeah, absolutely. It's there just to make sure that you're localizing, and it doesn't really. It might be interesting once if you start with asking questions about what are the observables we can do locally, point like operators, or extended things that can be integrated over cycles. And that, of course, would be a fascinating follow-up because the mathematicians have accumulated a huge amount of beautiful results about what happens with various minimal cycles, wrapping cycles in the target, and co-evolving together with the geometry. And they've used those actually as probes that allow them to control some of the singularity behavior. So those would be excellent probes in terms of topological particles or topological strings or topological membranes. And they should share this type of topological symmetry. They should show up both on the side of being allowed as topological observables, being BRST closed, and should have their own more volume descriptions. But that hasn't been worked on at all so far on the physics side. So this is still the somewhat pedestrian part, but as a physicist, I would now say, fine, we have this starting point, we have the foot in the door, we can reproduce at least Hamilton's flow out of the localization of the topological field theory, but it's still not yet as interesting because we haven't added as many gauge symmetries as we can meaningfully think of as physicists. And I would say, based on what I know about non-relativistic gravity, I still want the theory to be invariant under foliation preserving space-time diffeomorphisms. So for starters, we do have spatial diffeomorphisms, but they are so far time independent as symmetries of that minimal primitive theory. So now we'll gauge these spatial diffeomorphism symmetries. And that's typically accomplished by introducing in the bosonic gravity theory, kind of remembering that if you think of the spatial metric as a part of the ADM variables in GR, then the rest of the space-time metric consists of the lapse and shift variables. And the shift variables are the ones that gauge time-dependent spatial diffeomorphisms, and the lapse function is the one that gauges time reparametrization. So we'll follow in the same steps in order to gauge, in order to allow this spatial diffeomorphism to be a time-dependent symmetry. We introduce the shift vector at the bosonic level. It will transform as usual under this time-dependent spatial diffeomorphism. So you see that the reading piece indeed concurs with NI transforms in the gauge field under C. It also has this extra improvement set of terms to guarantee that NI is also a spatial vector field. And in the supersymmetric context, we of course want to be embedding everything into a supersymmetric n=2 setup. So I'll promote the spatial time-dependent diffeomorphism transformation into superfield. Of course, here you start having options, and we have called the basic three options C, A, and B. And that stands for if you make this diffeomorphism and appropriately, then also the shift vector chirality, meaning that E bar superderivative would annihilate this. You can call it theory type C for chiral. If you impose instead the anti-chirality condition, you call this theory type A. And then finally, if you allow the theory to have both chiralities, so it's a balanced theory of the type that we started with, it will be called type B for balance. And all three are interesting independently of each other because, remember, normally you would say, oh, there's only a cosmetic difference between Q and Q bar. I can change variables in such a way that they play each other's role. But that's only true up to the point where you decide which one of them is the BRST charge. Once you declare Q to be the BRST charge, then it's no longer true that the chiral and anti-chiral theory would be the same because you no longer have the freedom of relabeling Q and Q bar. So these three are three different versions of the theory, much like, for example, the topological sigma models in topological string theory have the A model and the B model version. So now we have also the shift vector promoted into a superfield. In order to covariantize all the derivatives, turns out we have to also introduce fermionic superfields, which will, just like Ni, will covariantize the time derivative, and therefore just the naive time derivative of the metric will be promoted to a covariant derivative by supersymmetric extensions of the standard covariant derivatives using the shift vector in GR. The superderivative and the bar superderivative are also promoted to covariant ones, where you now have superfields Sk and Sk bar, which are starting as a fermionic lowest component superfield. And in order not to have too many extra component fields in this setup, you have to impose constraints. So we found these nonlinear constraints, first by inspection, and then by, in retrospect, realizing that these constraints are somewhat surprisingly just super Yang-Mills constraints in the sense that I'll explain in the next transparency. So just to explain again, we will have three superfields, each of them in the type B maximum setup. There's 4 components, but there are so many constraints among them that only 4 out of these 12 components are independent, and those are exactly the shift vector, 2 superpartners, and an auxiliary field. So the geometric interpretation was actually, first of all, if you look at the constraints, again, as I said, you can derive them from scratch by just requiring that these derivatives satisfy some reasonable superalgebra, and then you don't end up with too many spurious components that would carry some additional gauge invariant information that you don't have any interpretation for. But in retrospect, these are just the conditions of the vanishing curvatures on super time. By super time, I mean, imagine that this super manifold is actually fibered over a 1/2-dimensional superspace consisting of the time and theta theta bar. Let's call that super time in the absence of a better name. And then the covariant derivatives actually on that super time after the covariantization satisfy exactly the same commutation relations as the uncovariantized previous one. So that means that the curvature, which will appear here as an obstruction against this closure of the algebra, are actually all 0. It's actually even better than that, because these W are just formally defined as whatever obstructions against this closure would appear on the right-hand side. But then, to my surprise at least, we found an even more accurate geometric interpretation of this construction. It's on the nose identical to constructing a supersymmetric Yang-Mills. And that might be actually interesting, coincidentally, for completely different applications. I've been speculating that perhaps this might be useful for the famous DCJ duality between color and kinematics in even non-supersymmetric field theories developed by Weber and company. I'll tell you why if you are interested, but let's first review what actually the construction exactly is. So now I'm asking you to think of your underlying space-time for a change as only the supertime. So this is a space-time of dimension 1/2. And then you postulate that on this 1/2-dimensional superspace, you write down super Yang-Mills gauge theory following just the conventional standard steps, meaning you introduce for each of these 3 supertime dimensions, you introduce the appropriate superconnection superfield. So there are 3 components. There's some internal Yang-Mills index A. All these fields depend as fields only on T, theta, and theta bar. And then, what is the internal symmetry index A? It's a multi-index consisting of where you are on the transverse spatial slice, and you pick a vector index. In other words, it's the algebra, it's the adjoint representation of the algebra of all smooth spatial diffeomorphisms of the slice sigma. There's certainly a Lie algebra formally defined. It's infinite dimensional, but it satisfies an honest Lie algebra where the structural constants are not field dependent. You can write down what they look like in terms of delta functions, and then you just follow the standard prescription. You take these super connections, even though the adjoint index is infinite valued now, you can impose just the conventional standard constraints on super Yang-Mills, and you get exactly the construction we found before. I find this remarkable because this is the first place where I see, for a long time, any very clear connection between gravity symmetries and Yang-Mills symmetries. Because gravity is a gauge theory, but the analogy with Yang-Mills only goes so far. It usually breaks down sooner or later. You just have to face up to the fact that your symmetries are geometric symmetries of the underlying manifold rather than internal space symmetries. But this non-relativistic split between time and the rest of the symmetries, the rest of the dimensions, allows you to reinterpret at least the spatial diffeomorphism part of the gauge structure of gravity. Even in the bosonic case, you could run the same argument to get about supersymmetry. This would work for the bosonic construction as well. And you can actually associate an honest Lie algebra, closed Lie algebra without field-dependent structure coefficients that looks like an honest internal Yang-Mills algebra with spatial diffeomorphisms. And that's, in some sense, an ingredient that BCJ story seems to be calling for. So I don't know if this is the missing ingredient, or I don't know if there's any connection to the structures required by BCJ, but I find this analogy remarkable.
And it's still a flat connection.
Yeah, it's flat on the supertime. So you could do the bosonic thing and say, of course, my connection has to be flat on time if I'm choosing an artificial non-relativistic split and saying I should think of the shift vector of GR as a connection on just the time direction with the location where the shift vector is in the transfer space being the internal Yang-Mills index. So it will have to be a flat connection, but the fact that the algebra closes and the structure follows just the conventional set of constraints, I think that's hinting on some importance. I'm not sure what it's going to be useful for, but I found it surprising. Okay, the action for this slightly fancified theory is going to be very similar as before, except now I'll be putting invariant derivatives instead of the original superderivative in here. And the action is in the superpotential term, again, still very similar. So this doesn't seem to buy you much, but it does buy you one thing, and that's the Deturg's trick, because Deturg's trick is now clearly interpreted as the possibility of choosing various gauge fixing conditions of this newly promoted spatial diffeomorphism gauge symmetry. Previously it was just a global symmetry independent of time. Now you can think of at least 3 different gauge fixing conditions shedding light on various different aspects of the flow story. But that's not such a huge step forward. The more interesting step forward will come from finally gauging also time translations. So far the theory is only invariant under rigid constant time translations by some fixed amount of time. Just like in the case of Ricci's gravity in the bosonic story, the maximum gauge symmetry there contains time reparameterizations as a local gauge symmetry. So why not allow also those time reparameterizations? That's where the fun begins, because this will now turn itself into an honest gravity theory along the time direction rather than being more like a matter system on spatial slices. And it's nice to have the lapse function, which will be the gauge field for the time reparameterizations as a part of the ADM field content, because then these fields, before the topological gauge fixing, the fields that you have are precisely the ADM variables of general relativity. So this is even closer to what we understand as standard gravity theory. So the lapse function can be introduced in the bosonic case as this famous transformation property, again indicating that log of n essentially behaves as a gauge field of time translations. Here we again want to make everything consistent with supersymmetry, so it chooses a completely unconstrained superfield of time reparameterizations instead of looking at the chiral or anti-chiral version. So those would exist too, but this is the more interesting scenario. And then we start covariantizing the derivatives under time reparameterizations. Turns out we have to introduce new superfields in order to turn the previously covariant derivatives into even more covariant ones that are now nicely transforming under time reparameterizations. So first we have to introduce a superfield E. It's called E for a reason, I guess, because it's going to be one of the, in retrospect, one of the components of the inverse field line. And then you find out in order to covariantize the superderivatives, you also have to introduce 4 additional superfields. And then you have to follow the same strategy as before, impose enough constraints so that this new lapse superfield sector doesn't have too many spurious components which will carry gauge invariant information. So it turns out by inspection that these are the correct constraints, and I've already set B equal to this curly E equal to curly E bar equal to 1, there's a very small loss of data by that. Turns out that these curly E's and E bars have to satisfy on full spacetime in the presence of shift vectors a covariant time constancy condition, which says basically they have to be constant along the lines of the flow of the shift vector. But for simplicity, we can just set them equal to 1, which is not costing us much. It's also just viewed as a normalization. You can say I'm covariantizing this previous superderivative D by adding an important shift piece here. So I can normalize this E to be 1. And then once you introduce these theta bars, those have to be constrained in a nonlinear fashion, and they themselves determine what this original capital E was. So it's a similarly complicated set of constraints as before, but it's an even more interesting question to ask. So far, we've introduced these fields to match the dependence of the gauge transformation on space and time. In particular, it's consistent, just like in Bolzani-Lipschitz gravity, where you can impose a condition that the lapse function is only a function of time. It's a so-called projectable field. It lives only on time. It can be pulled back on full space-time. That's a consistent limit of the full Lipschitz theory of gravity. But nobody's forcing you to take that limit. You can allow the gauge field, the lapse function, to be dependent on space-time. That's in some sense more desirable because, first of all, it's a more generic theory. Also, it's closer to the field content of general relativity, if that's what you're interested in. So that it's a non-projectable version where the lapse function is a function of space-time, even though it's transformed only by time reparametrization gauge symmetry. That's the more desirable version. So far I've listed the constraints only for the projectable version, where all these fields are only a function of super time, not of the transverse spatial direction. Now I can prove that we can extend the theory of these superfields to the full non-projectable case. So they're now allowed to be all functions of space as well as time and theta bar, just that the constraints become more complicated. So for example, the constraint that tells you what heat is in terms of all the other ones, now in the presence of all the other stuff and allowing fields to be space-time fields becomes this constraint, and the other ones similarly generalized. So that wasn't guaranteed that the non-projectable extension would exist. That could have been an obstruction. And I'm very pleased that there is no such obstruction. We were able to find this generalization. It's important for us because now we can finally do something interesting with the action. We can again write it as a kinetic term and a superpotential term. The kinetic term will be just the obvious ones. You just have these newly supercovariantized superderivatives in there, but other than that it's the same. The novelty comes from the superpotential, because famously in non-projectable Lipschitz gravity, when you take the lapse function and it's a space-time field, it now carries some non-trivial gauge invariant information. There are new gauge invariants that you can put into the action. In particular, if you ask what is the full list of up to two derivative operators that I can put into the action, you have not just the scalar curvature, but you can now take the spatial derivative of the log of the lapse function, square it using the inverse metric, and that's a new term in the action. That's a very important term in the phenomenology of Lipschitz gravity, as well as in Lipschitz holography, where this term actually explains why you can do holography for non-relativistic systems using just the bulk Lipschitz vacuum gravity instead of having to add matter fields. But here it has a very different important role to play, because now when you stare at this superpotential, you realize that it contains exactly the same features that Perelman's F functional contains. If you identify basically the Bolzanized limit, or this object that I call the W when you just replace these with Bolzani fields, that would be Perelman's F functional when you turn off the cosmological constant, for reasons which I haven't explained why that should happen. And you just set these two couplings equal to each other. And if you interpret Perelman's dilaton to be R phi. So R phi, the log of the lapse function, is the dilaton of Perelman's equations. And that perhaps is an interesting novelty, because so far I haven't seen any interpretation of the Perelman dilaton other than in it's a candidate development field in some more complicated one. Yeah.
What are you doing with the measure when you say that? Because the permanent action looks exactly like the integrand, but not, you still have to do it to theta.
Well, what we really want.
Are you looking at the part with dt theta eats up n or something?
You can define again the same W as before, and it's not important.
Oh, because it's, okay.
The flow equation,
Not the equation.
the flow equation will be coming from the bosonic part, the lowest component of this. So this is strictly on the node, n is e to the minus phi. So if you say phi is exactly permanent silicon, it also explains why it's e to the minus phi and not different exponentials in front of the two terms, because we are constrained by time reparameterizations. In parallel with quantum field theories, these choices of couplings will look like fine-tuning. Because why you have one particular function of the dilaton in front of one and another different function in front of the other term. There is no symmetry apparently. To us, the symmetry is time reparameterization invariant. So I think this is quite a crucial ingredient in the construction. I think I'm starting to run out of time, so let me see what are the most important highlights of what I want to stress. So now we have identified tentatively the Labs function, or the log of the Labs function with the dilaton, and we see at least vaguely resemblance to the F functional. We can make it more precise by just deriving the localization equation. And that's where we should or should not see the match to the permanent flow equation. So when you derive the localization of the non-predictable theory, you get this equation, which might be the reason why it took us several weeks before we figured out how to get from such a complex equation to just a simplified permanent setting. So it looks like it's a multi-parameter generalization of permanent, but where is the permanent limit in this? And in particular, you notice that even when I'm comparing these white terms are the ones that permanent has. So this, and that is what I want to end up with. And there's clearly already a discrepancy. We have e to the phi in front of this left-hand side, but not in front of the right-hand side white terms. But that's an easy fix. You just say I have to change variables. I perform a change of frame. I define a tilde frame by rescaling by e to the phi, which fixes this discrepancy, apparent discrepancy. And then I also have to re-normalize what I mean by the dilaton in order to get permanent normalization. And once you perform that transformation, you still have a lot of junk on the right-hand side. And when you stare at that lot of junk, you have to remember that in order to get permanence equation, he had to impose a fixed measure condition. So this in his frame was fixed. When you rewrite in our original variables, our original metric, it turns out this condition now simplifies tremendously. It's just the constancy of the spatial volume of our original metric. And we know how to get this dynamically. This doesn't have to be imposed. I thought for a long time this would have to be a gauge fixing condition. You don't want to use it as a gauge fixing condition because then you're using up one of your D spatial diffeomorphisms, and you want to reserve all D of them to perform the Turk trick, not to keep D on -1 only. So I'm very glad that this doesn't come out of a gauge fixing condition. Instead, it comes out of a very well-known bosonic construction. In the bosonic Ricci gravity, you get the constancy of the spatial volume exactly dynamically as one of the equations of motion in the limit where the little lambda parameter in the action goes to plus or minus infinity. So it's a unimodular spatial condition. That's one of the equations of motion. It comes from the limit where this little lambda tilde parameter goes to 1 over d. So if you see where lambda tilde appears everywhere, if you set that equal to 1 over d, the equations simplify in permanent variables to just the sum of the two permanent equations. So long story short, this is one of his equations being equal to 0. This is the other of his equations, and they are blocked together by a very specific relative coefficient. Of course, the scalar one is multiplied by the metric itself, so that this entire thing is traceless. And that's the closest you can get to permanence exact equations in the context of a theory which still has the full time reparameterization invariance. Remember that permanence equations are not time reparameterization invariant, so you cannot split this naturally into two separate equations until you gauge fix also time reparameterizations. And that can be accomplished. Long story short, I can just say, oh, yeah, without any I don't even have any equation here, but it's true that if you perform a slightly modified gate fixing, which already also in one swoop fixes the time reparametrization, then you can get exactly this as one equation and this as the second equation in the limit where lambda goes to minus infinity. Norman also introduced something known as the W functional, which is a fancified version. I can just show you that we know how to get into variables where we reproduce the same functional from our superpotential and the appropriate equation of motion for either the shrinking or the expanding solitons. The F functional is best suited for static solitons, but for the expanding and shrinking ones, the appropriate functionals W and W plus can also be found with just our superpotential.
What are you calling them solitons?
They are calling them solitons. It's just some random mathematical terminology. They say if we have some spatial metric which satisfies certain conditions, it can be plugged into an ansatz that then satisfies automatically the Ricci equation. So they call that spatial metric a soliton. I don't find any particular insight in that terminology. I'm not sure why that's a good name, but it's commonly used in the math literature. Okay, so just to give you at least one drawing, since I'm out of time. A typical geometry in Perelman's frame would look like this. There would be these spherical branched topologies that would collapse to a complete singularity extinction point in finite time. There would be some hyperbolic ones which would keep expanding forever. And along the way there would be a lot of controllable topology change. These pinching singularities of codimension 1 would happen. In our frame, it's interesting to redraw the same type of generic evolution, because remember, this here has not just the metric, but also a dilaton does the compensating thing so that the system of equations is simultaneously satisfied. And when you perform this dilaton-dependent change of frame, like you would do in string theory where you go between the string frame and the Einstein frame, in our frame, that same geometry is actually quite interesting. Turns out because of the rescaling by the dilaton, the sphere parts, they still form pinching singularities. That pinches happen in finite time. But once there is one of these round-ish positive curvature spheres that pinches off into a separate baby universe, it actually ends up being just round and static. So it becomes an Einstein static universe. It doesn't collapse into a singularity in our frame until you reach infinite, well, not even in the limit of infinite proper time. When you measure the proper time here, it's infinite, and the solution becomes asymptotically static at a fixed finite radius. Similarly, the hyperbolic ones get rescaled by the reframing, and they also become static. So, of all the singularities, so remember in Perelman's story there were these two types of singularities: the extinction singularity or positive curvature piece, and a topology change. We keep the topology change, but we don't see the extinction. So that makes me hopeful that the theory is actually somewhat friendly to unitarity, where you don't lose even just a small number of topological states in your small Hilbert space because you don't have propagating gravitons. There is no sense in which you lose information by extinction events. You can always find some static branches where things are just put out to pasture. They live happily forever in a static universe. So to conclude, I'm out of time, I think we've found an exciting connection between three previously unrelated fields: topological quantum field theory, mathematics of Ricci flows, and non-relativistic quantum gravity. And we have a long list of possible interesting follow-up questions, some of which, the ones that are most interesting to me are perhaps whether the control over the topology change that the mathematicians are providing for us can be reframed as a short distance completeness of the theory, even without including z equal to 3 terms, say 3 plus 1 dimensions. What does it mean, in other words, for the theory to be complete? That means being able to say what is the answer to any meaningful physical question for physical observables as I zoom in to shorter distances, higher energies, maybe in some sense, even though this is a topological theory, there might be a sense in which you encounter new features at short distances, and then that indeed happens in the vicinity of these topology changing processes. So if you are zooming in on short distances in a generic part of the geometry, you just see asymptotically a flat empty space. So for that, we don't have any need to explain anything. There's no scattering you can probe this with, so there's no local observable associated with a non-singular space. But if you zoom into the vicinity of the singularity, you don't see a flat empty space. You see one of these models of the singularity. But those always, first of all, they're fully classified, so you always know exactly that the mathematician can give you a prescription how to uniquely continue past this topology changing event. And also, interestingly enough, they dimensionally reduce effectively to 2 + 1 dimensions, which happens to be the power counting normalizability dimension of this prediction setting without including higher derivative corrections. So I suspect that there might be even some connection between what we mean by power counting normalizability and here the full classification of the singularities, that you can provide any answer to any question about the short distance behavior of the theory just by borrowing from the mathematical literature. But you can pick your favorite from these 4 questions. I think they're all very interesting. So I'm going to stop here.
Maybe time for one question, then we can have more questions after. Yeah.
Has anyone looked at the possibility of including a two-form potential, Coulomb field, so to speak, into the flow equation?
I think people have looked into adding the B field in the RG interpretation of the equation. I'm not sure if they have gotten very far. I haven't seen it really play an important role in the math literature. Though that would be an actual step. If you are already suggesting the duotone, then you should be also adding the B field, and maybe that informs the mathematician even more about what is the interesting generalization of the flow. But I haven't seen any substantial literature. That might be just my ignorance, but the literature is vast. So there might be works that I'm not aware of along those lines.